All right, section 1.2 is transformations of linear and absolute value functions. So what we're going to do here is we're going to look at some translations here. So I'm going to use tables for all three of them, and we're going to see what happens. So on the first one here, I have, again, let's go ahead and say -2, -1, 0, 1, and 2. And if I do that, remember, absolute value changes changes negatives to positives, and positives stay the same. So if we look at that one here, when 0, 0, 1, 1, -1, 1, 2, 2, -2, +2, and we'll have something like this. All right, now let's go ahead and look at the next one. So the next one we have the absolute value of x plus 1. So I'm going to say -2, -1, 0, 1, and 2. Now on this one here, think of what's going to happen. So I'm going to go -2. The absolute value is that's 2 plus 1. That will give us 3. Okay, the absolute value of -1 is 1 plus 1 is 2. And then I'm going to have 1, 2, and 3 here. So again, when it was at 0, it's going to be at 1 this time. And then everything else is going to be still symmetrical. It's still a V shape. So even though I don't have all of those points, you know those are my points. All right, and then my last one here. I'm going to go again, -2, -1, 0, 1, and 2. So in the beginning, it's like the absolute value of, it's inside the absolute value. So I have -2 plus 1 is -1. Absolute value of -1 is 1. And again, -1 plus 1 is 0. 0 plus 1 is 1, 2, and 3. But again, the same kind of thing here as I just told you earlier. All right. If I look at 0, it's going to be at 0 and 1. And then when I plotted the other points, again, since it's symmetrical, ladies and gentlemen, again, you should have something that looks like this. All right. So now, what's the key here? From the graphs, we can conclude that f of x minus h. So this one right here, they're saying I can write this as x minus h. So that would be x minus a -1. So that would give us an h of -1. All right. So if that's the case, if it's a negative h, it will go to the right. If it's a positive h, it'll go to the left. And I kind of hinted at that today. So subtract h from the input before evaluating the function. On f of x plus k, that gives us a vertical shift. So that would be this middle one. So that is going to be f of x plus k gives us a vertical shift of, when it's positive, it's going to go up, which it was positive, so it went up. And if it's negative, it's going to go down. So add k to the output. Again, I kind of hinted today, think of this as inside x, outside y. And that's for translations. All right, and we're going to see this a lot. So when I say inside x, it's inside a parenthesis of some sort. Okay, an absolute value is kind of a parenthesis. Think of it that way. Okay, so our first example, let f of x equal 4x plus 9. Write a function whose graph is a translation 5 units up of the graph of f. So what this is telling us to do, just what I showed you here just a second ago, is it is asking us to add 5, right, to each output value. All right, so your book kind of likes to use g of x a lot. So we're going to say f of x, which was our regular one, and we're going to add to that on the output. So we're going to put it on the outside, all right? So if we look at this, our f of x was 4x minus 9, and then we're going to add our 5 to that, and well, negative 9 plus 5 is negative 4, so I'm going to have 4x minus 4. All right, part B, write a function h whose graph is a translation 1 unit right of the graph of f. So on this one here, they said write a function h. So if I write a function h, I'm going to say h of x, and I just told you it was in the right, so we're going to say f of x minus 1. So remember, I told you what's going to happen is we're going to attach it to the x and put parentheses around it. So if we look at that, we're going to have f, wherever I see x, I'm going to replace it with x minus 1, and then I still have that minus 9 on the outside. All right, now, by our distributive property, you would tell me this is 4x minus 4 minus 9, and then to combine the two there, we'll get 4x minus 13, and that's our final answer. Excuse me. So our reflections in the x-axis, it's going to be, the negative is going to be on the outside. So this kind of doesn't do the inside x, outside y, if you want to think about it that way, okay? But it's always going to be on the outside. When it's in the y-axis or over the y-axis, it's going to be on the inside. All right. Sometimes you can use both of them, and I know in trigonometry that's what's happening right now with this. So again, I just said inside x, outside y doesn't apply here. Okay, but it does for everything else. All right. So A, write a function. So example 2, excuse me. Let f of x equal x minus 5. That's in the parentheses, minus 4. Write a function h, so we know it's going to be h of x, whose graph is a reflection in the x-axis. If it's a reflection in the x-axis, what it tells us is we're going to take that negative, and we are going to now have a negative of f of x. That's on the outside. So on this one here, we're going to take the negative, all right? Then I have the absolute value of x minus 5 minus 4. All right, now when I'm distributing it through on this, ladies and gentlemen, when it's an absolute value sign, you are not going to distribute that negative through the absolute value. You're just going to put it in front of the absolute value. So we're going to put it in front of the absolute value, and then I have my x minus 5. But here, a negative times a negative is a positive. So that's our final answer on that one. For B, write a function g whose graph is a reflection in the y-axis. So on this one here, we're going to say g of x is equal to f. When it's in the y-axis, the negative is attached to the x on the inside. All right. So again, wherever I see x, I'm going to replace it with negative x. All right. So I see it that way. And I believe that one it will accept on the homework. So that's the way I'm going to keep it for you. All right. So we're done there. All right. Now stretches and shrinks are pretty straightforward. We talked about vertical, but now the one we need to talk about is the horizontal stretch and shrink. The easiest way to remember a horizontal stretch and shrink is that whatever number I have, I'm just going to flip it. All right, I'm going to do the reciprocal of it. Okay, so On this one here, the graph of y is equal to f of a of x. Notice it's on the inside. It's inside x. Is a horizontal stretch or a shrink by a factor of 1 over a of the graph of y is equal to f of x, where a is greater than 0. Remember, if I have a negative out there, that's going to tell us we have a reflection in the x-axis. All right, and a cannot equal 1. Multiplying the inputs of a before evaluating the function stretches the graph horizontally away from the y-axis when a is between 0 and 1, and shrinks the graph horizontally towards the y-axis when a is greater than 1. So they had this one here. This is in your textbook, all right? It didn't copy very well, so I do apologize for that. But it's kind of saying the same thing. So just kind of pay attention to what I'm talking about, because we're going to see these a lot again, ladies and gentlemen. I keep hinting on that, all right? And we just did the vertical stretch and shrinks earlier. Here's one interesting thing is on horizontal stretch and shrinks, the y-intercept stays the same. On verticals, the x-intercept stays the same. So on this one here, the graph of y is equal to a times f of x. So it's on the outside. Is a vertical stretch or shrink by a factor of a of the graph of y is equal to f of x, where a is greater than 0 and a is not equal to 1. Again, multiplying the outputs on this one here, it was on the inputs because it was inside the parentheses. On here, it's outside the parentheses. So multiplying the outputs by a stretches the graph vertically away from the x-axis when a is greater than 1, and shrinks the graph vertically towards the x-axis when a is between 0 and 1. So example 3 here, let f of x equal the absolute value of x minus 1 plus 2. Write a function g whose graph is a horizontal stretch of the graph of f by a factor of 5. So whenever you hear horizontal, this is my key to you. Whenever you hear the word horizontal, you're going to flip it and you're going to attach it to the x. So we are going to say g of x is equal to f of 1/5 x. All right, so that tells me what I just said earlier. Wherever I see x in f of x in our original function, I'm going to be replacing it with 1/5. So wherever I saw x, I see x right here. So I'm replacing that with 1/5 x. And then everything else stays the same. B, write a function h whose graph is a vertical shrink by a factor of 25/100. So a vertical shrink is on the outside. So h of x, because that's the one they told us to do, is equal to 0.25 or 25/100 times f of x. All right, so we're going to take our 25/100 and we're going to multiply it to our absolute value of x minus 1 plus 2. Just like I told you, we don't take a negative through the absolute value. We also don't take the 0.25. It stays on the outside. So when I take that, I'll have 0.25 or 25/100 of x minus 1. But if I take 0.25 times 2, which I can, I distribute it to both of them, but just right here, I'm going to put it in front. Okay. So 0.25 or a fourth of the 2 is equal to 1/2 or 0.5. And don't worry, we're going to spend a couple of days on this stuff. So we're going to do a worksheet tomorrow on this. Well, the next day. Finally, you can write a function that is a combination of transformations. So our last example here, let the graph of h be a horizontal stretch. Oh, what did I tell you about horizontal? Think about that. By a factor of 8 and go by the way they're telling you. Then after that, they want you to do a translation 10 units down of the graph of f of x is equal to x. So write a rule for h. So on ones like this, they told us to do one thing, and then they told us to do another thing. So on this one right here, we have two things. Okay? So step 1, write a function g that represents the horizontal stretch. Okay, so when I do that, now your book likes to go, we start with f of x, and then they like, when they do something twice, they do g of x, and then they finish with h of x. So we are going to say g of x is equal to f. Remember, it's g of x is equal to f times a of x. A is on the inside, right? So we're going to say, in this case here, we have an 8, so I told you to write that and flip it, so it's going to be 1/8 x. All right? So again, this is what we started with, so that's what we end up with. So it's just going to be 1/8 x. Step 2, you're going to write a function h that represents the translation of g. So the second step takes and uses this one here. All right? So in this case here, it said 10 units down. So if we recall, that is going to be h of x is equal to g of x minus 10. There's our 10 down because it's outside. All right? So when I do that, again, our g of x from up above was 1/8 x minus 10. So that is our h of x. And I did both of them, so I'm all done. All right, we'll probably do a couple in class tomorrow, so make sure you watch this. Thank you.